Hello everyone, today we're gonna learn section 4.8 Lagrange multipliers. So Lagrange is a French mathematician, and Lagrange multipliers is one of the methods to solve optimization problem. So normally we had optimization problem, we are using maxima minima problem, right? But this is one of the method to solve optimization problem. So we have a constraint. So let's take a look. We have one constraint. We have two constraints when we use Lagrange multiplier. So constraint means it's a restriction or condition. So let's take a look. We have the function two variables, right? So we have this function. So this is optimization problem. And also we said objective function. Then we have another function equation, right? So we call this is constraints. Function constraints. Yeah. Okay. Now, example, we have maximum number of golf balls that could be produced and sold in 1 month. We have X, maximum number of advertising hours that purchased per month, Y. So this is what I said earlier. This is a constraint, right? And look, I set up this function equal to 0 because we can set up that function equal to C when we find level curve, right? So if we make a C, this one, then we can set up C equal to 0 or C equal to 150. Then blue is inside of that ellipse, right? That is, blue one is C equal to 0. And then the outside green is C equal to 150. Yeah. And we can draw bigger, right? So when C equal to like textbook say that 20, 250, 300, 395. We can do more, right? So I just a little bit lazy to type in here. All right. How do we do that then? How do we apply method of Lagrange multipliers? So first of all, we're gonna learn one constraint. So we have let two functions have a partial derivative, and then we set the original g function equal to 0, and then gradient is not the 0 vector. So we had a gradient, right? So this is the gradient. 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 Okay, so gradient is a partial derivative for vector function, right? So we did that before. Gradient. Partial derivative for vector function. Vector valued function, right? Okay. Then, okay, let's talk more. So the g function is equal to 0, and then gradient it's not equal to 0 vector, has a local extremum. It can be local maximum or minimum, right? at the point x naught, y naught. Then there is lambda in Greek letter. Lambda. So that's why we said that, not this way. So called the Lagrange multiplier. So that lambda is called Lagrange multiplier because we multiply with that lambda. All right. Okay. So let's take a look. This one we have gradient of f equal to multiply lambda with gradient of g, right? Okay, now we have previously gradient is normal to the level curve. So normal, which is perpendicular, right? So perpendicular. So we had z equal to the function. Function is continuous, first order partial derivative. So it's cut off partial. Let me see. Yeah. So partial derivative in the point. So gradient of f is now equal to 0 vector. Then gradient of f with the point is normal to the level curve of the function. Yeah. So we talked about this one in the last section. Actually, where is that? So I don't remember the section number. Is directional derivative and then gradient, that section, right? Okay, so let's do that. Find the minimum value of the function. So in that section, we distinguish that function is objective function. And then they say they're subject to the constraint. So we have a constraint function or just constraint, right? All right, so we have that. Now, this is a Lagrange multiplier method. The formula, right? Okay, now let's find out left side gradient of f. So gradient of f is, we find the partial derivative. Let me write down the formula here. Okay, so I brought up the formula for gradient, what we did the last time. And then here is the steps for how to find Lagrange multiplier, right? So we have to set up the form from the formula, right? And then this is a constraint function, right? So this is a constraint. So we set equal to 0, and then we start for x naught, y naught, and then we substitute. Then we need to find the largest one or smallest one. It depends on. All right, so since in this problem they ask us minimum, then we need to find the minimum, smallest number. All right, okay, let's do it. First of all, we need to find the partial derivative with respect to x from the objective function and partial derivative with respect to y from the objective function. And then we keep the vector value, the function ij, right? Okay, so let's do it. Partial derivative with respect to x, 2x minus 2 I, and partial derivative with respect to y, 8y plus 8j, right? Okay. So we have some gradient of f equal to, let me just write this way, right? Sure way. Okay, then the left side we have 2x minus 2i plus 8y plus 8j, right? J hat. And then we need to find gradient of g. So from here, partial derivative with respect to x, we have 1, I, right? Partial derivative with respect to y, 2j, right? Okay. I plus then lambda I plus 2j, right? Okay. Now, we want to multiply. That's why I call the Lagrange multiplier, right? So let's multiply. So we have left side, just copy, lazy, copy, paste. And then right side, we will have lambda I plus 2 lambda j, right? Okay, so look, they are equal each other. Left side, the right side. Then look, I with I, J with J, right? So they are corresponding each other. So we can say that 2x minus 2, I with I equal to J, lambda, right? J with J. So 8y plus 8 equal to 2 lambda, right? So let's using that. So that is 2x minus 2 equal to lambda, and 8y plus 8 equal to 2 lambda, right? Okay, right equation, we can divide by 2. So divide by 2. So we have 4y plus 4 equal to lambda. Yeah. Okay. So we say that we can say lambda equal to lambda, right? Same. 2 equal to 2, 3 equal to 3, 100 equal to 100, right? So we can say lambda equal to lambda, right? So we have 2x minus 2 equal to 4y plus 4. Okay, now let us solve for x. Either way, you can solve x over y, right? So let's start for x. Then we have 2x equal to 4y plus 4 plus 2, right? Which is 6. Now, I'm going to write down so you know that. Okay, now x equal to divide by 2. So we have 2y plus 3. Okay, so this is x equal to, right? And then they say that we can make the constraint, they make a function because we name that 0 x naught, y naught, right? So this one we can make a 0, right? So let's substitute into the g function. So we have a constraint, which is this one, right? Okay. We have equal to 0, right? All right. Now, we can substitute substitute into the g function x equal to 2y plus 3, right? So that would be, so we have 2y plus 3 plus 2y minus 7 equal to 0. Okay, now we can solve for y then, right? This time, solve for y. So we have a 4y minus 4 equal to 0. Then y equal to 1, right? Okay, now let's substitute into the constraint, right? So we have 2y, not constraint, the x equal to, because we need to solve for x, right? So how about, do we need a label? Okay, let's make a label. So this is equation number 1. So substitute equation number 1. So we have x equal to 2y plus 3. So substitute. So we will get 2 times 1 plus 3, which is 5. Okay, so xy, then we get x equal to 5, y equal to 1, right? All right, so we want to know about whether which number, which value is the minimum, because we don't have to worry about is it maximum or minimum, right? So just the minimum we need to find. So since we have objective function, so this one, we can just substitute when x equal to 5, and y equal to 1. So we have 5 squared plus 4, 1 squared, minus 2 5, times 5, plus 8 times 1. Then we have a 27. That would be minimum. All right. Okay, but then let's ensure that that is the minimum value. So let's using constraint function. So we have this constraint, right? Equal to 0. All right, so we knew that this is originally from x plus 2y equal to 7, right? All right. So for x-intercept, how do you find? Set y equal to 0, then x equal to 7, right? So we get 7, 0. For y-intercept, set x equal to 0, then we have 2y equal to 7, which is y equal to 7 over 2. So we have 0, 7 over 2. Then let's say evaluate, right? So evaluate from the objective function. Copy. Evaluate. So f of 7, 0. Then we have a 7 squared plus locally 0 there. And we have negative 2, 7 equal to 35. Good. F of 0, 7 over 2 equal to, luckily we have a 0. That's why we picked that x-intercept, y-intercept. So 4, 7 over 2 squared plus 8, 7 over 2. What again? 77. Okay, so why we pick the x-intercept, y-intercept? So this is x-intercept. And this is a y-intercept, right? So this is the line. Look at the line. That's the constraint function. So x plus 2y equal to 7. And this is objective function. Constraint objective function, right? And then let's take a look 5, 1. That is the minimum, right? So we conclude this is a minimum earlier. But then why we ensure to pick the x-intercept, y-intercept, right? So look, this is a y-intercept. Which is above 5, 5 and 1, right? And this is x-intercept, which is below 5, 1, right? 5 and 1, right? So even though we evaluate the below 5, x is 5 and y is 1, which is x-intercept 7 and 0, right? What do you get? 7, 0. Then we get 35 above here, right? And then y-intercept, even though we evaluate 0, 3.5, which is 7 over 2, we get also 77. So we can conclude, hey, this is to make sure. This is the 27, which is the minimum. Make sense? Why we pick the x-intercept, y-intercept, right? So this is for sure. This is the minimum. Oh. Move a little back. Thus. You guys okay with this? Very good. Yeah, by the way, the C is the random number, 10 and 26, right? So this is a C. This is a C, random. Okay, now, what if we have 3 variables? So Lagrange multipliers with 3 variables. So same, I'm missing that constraint equal to 0, right? So I'm missing that. So let me write down constraint function equal to 0. So g of x, y, z. They're using x naught, y naught, y naught, x naught, y naught, z naught equal to 0, right? Ooh, careless. Okay, z naught equal to 0. All right. Okay, let's do this example. So we have objective function and constraint function. So this equation constraint, and then we make a constraint function then using function notation, which is g of x, y, z, right? Equal to that, right? All right, now we are using same strategy. What was the strategy, right? So step 1, we take the gradient of the function of f, which is objective function, and equal to, we are making Lagrange multiplier lambda there, and then multiply with the gradient of g, which is what is called constraint function, right? Constraint function. Since they're using g, I'm using function. Then we make the constraint function equal to 0. Then we need to solve for x naught, y naught. Then we evaluate those numbers, right? So evaluate. So evaluate. Evaluate, correct, right? X naught. How about f of x naught, y naught, right? F of x naught, y naught. Then it depends on question. Maximum, then we say maximum. Minimum, then we say minimum, right? But we have to ensure that the maximum minimum. So we test out couple points, right? Okay, let's do it. So we have the function. So let's find out gradient. So let me see, copy, paste. All right, so what do you get? The partial derivative with respect to x, 2x, good. I, partial derivative with respect to y, 2y, j, partial derivative with respect to z, 2z, k, right? Good. Equal to lambda. And then we're looking at the constraint functions. So partial derivative with respect to x, it's 1. I, right? So 1i, which is I. Yeah. I had. Okay, partial derivative with respect to y, also one I, oh, sorry, one j, so j hat and k hat, right? All right, let's distribute. So right side we have lambda I hat plus lambda j hat plus lambda k hat. Let me copy left side. Okay, now what is the corresponding left and right, right? So we can say that I with I, J with J, K with K, I corresponding, J corresponding, and K corresponding each other because equal sign, right? Okay, now that is 2x equal to lambda, 2y equal to lambda, and 2z equal to lambda. Yeah, all right. So like earlier, lambda equal to lambda. But we have three variables, lambda equal to lambda equal to lambda, right? So uh, lambda equal to lambda equal to lambda. The first lambda equal to 2x, second lambda equal to 2y, third lambda equal to 2z. Let's divide by 2. So we have x equal to y equal to z. All right. Now, from the constraint function, we need to solve for x, y, z. So we have this one. Let's make that. Copy. Okay, so in order to solve for x, either one, y or z, you can pick anyone, right? Anything, not anyone, anything. Since we say that x equal to y equal to z equal to, right? So we can say this one, x equal x plus, since y equal to x, x, since z equal to x, x, right? Make sense to you? All right. So, hey, we have to make this one. What I'm doing. So let's see. X plus X plus X. Yeah. Okay. Now, instead of equal to 0, normally we set equal to 0. Let's make a set equal to 1. Negative 1 move to the other side, right? So we have a 0. So there will be equal to 1. So going back to original constraint, so equal to 0. I mean, no, sorry, equal to 1. Yeah? Okay. Now, solve for x. So 3x equal to 1. So we have x equal to 1/3. And since x equal to y equal to z, x equal to 1/3. So y equal to z, which is 1/3, right? So we have x, y, z, which is equal to 1/3, 1/3, 1/3. Make sense? All right. Let's evaluate. Let me see. Is it minimum? Yeah, it's a minimum, right? Minimum. So minimum. So the function, objective function, I should copy earlier. Copy. So we have f of 1/3, 1/3, 1/3, which is 1/3 squared, plus 1/3 squared, plus 1/3 squared, right? Okay. So can you please calculate? So this one, we have 3/9, which is 1/3, right? Okay, so we say this is a minimum, right? Make sure about this is a minimum. Let's set up the number randomly, right? So we have constraint function, right? So we have let me just copy from the original so that we can see easily. Copy. So we copy the constraint function, right? So this is a constraint function. Just constraint because we do not use function notation. All right. So when x equal to 0, y equal to 0, then z equal to 1, right? So there will be f of 0, 0, 1. Let's evaluate. Okay, so let me see. We have the function here. Yeah. So we get once, I'm sorry, 0. Yeah. You want me write down everything? Okay, 0 plus 0 plus 1 square, which is 1, right? How about when? Same concept, right? I don't have to write down x equal to 0, z equal to 0, then y equal to 1, right? So we have f of 0, 1, 0, then we get 1 as well, right? So when x equal to, how about y equal to 0, z equal to 0, then x equal to 1, right? So that is f of 1, 0, 0 equal to 1 as well. Okay, so everything is bigger than 1/3, right? So let's pick any random number. So when x equal to 0, y equal to -2, then what's the z? Z equal to 3, the random numbers, f of 0, -2, 3, that is 0 squared plus -2 squared plus 3 squared, then we get 13. So can you see that every numbers bigger than 1/3? So we can say that this is a minimum, right? Oh, I wanna make everything there. Make a little bit shrink. So copy this one. And let me just write that. Thus, f of 1/3, 1/3, 1/3 equal to 1/3 minimum. Okay. Okay, so we have Lagrange multiplier with two constraints. Okay, let's take a look. We have three variables. And then we have one objective function, and then we have two constraint functions, right? Okay, so same concept, but we will have two lambda. So look, we have a gradient of the objective function equal to, normally we have only one lambda multiply, right, with the constraint function. But since we have two constraints, so lambda 1, lambda 2, constraint, with the two constraint, we multiply with gradient of two constraint function, right? Okay. So we set up the constraint function equal to 0. Then we are looking for what is x, y, z, whether minimum, maximum, right? Okay, so let's do this problem. So find local extreme values of the function. So normally we had minimum earlier, right? But at this time they want us to find whether maximum or minimum, right? Okay, let's do it. First of all, we have to find gradient, right? Okay, let's follow that. Oh, sorry. Copy, paste. Okay, so let's take a look gradient of the objective function. So partial derivative with respect to x, that's 2x, I. And partial derivative with respect to y, 2y, j. Partial derivative with respect to k, I mean the z, so 2z, k, right? So let's write down. So 2x I hat plus 2y j hat plus 2z k hat, right? Equal to lambda 1. And then gradient of constraint function. So let's write down g equal to x squared plus y squared minus z squared, right? And let's make h. So normally we writing out g of x, y, z, because the three variables there, right? So h of x, y, z equal to x plus y plus minus z plus 1. Yeah, okay. Now we want to find the partial derivative. So this is everything same as this one except to the sign, right? So let's do it. That will be 2x I hat plus 2y j hat minus 2z k hat. Okay, now there is no space. So let's talk about lambda 2 plus lambda 2. Okay, partial derivative with respect to x, y, z. So there will be 1, 1, 1s. That is ij negative k, right? So we don't have to make that other. So let's make here. So lambda 2, I hat plus j hat minus k hat, right? Okay, now let's distribute. So we will have 2x lambda 1 I hat plus 2y lambda 1 j hat minus 2z lambda 1 k hat, right? Okay, the next term is plus lambda 2 I hat plus lambda 2 j hat minus lambda 2 k hat, right? Okay, so can we make a corresponding each other? How about let's make I with I, right? So that will be I, J, J, K, K, right? Okay. So 2x, 2x, lambda 1, I plus lambda 2, I had, right? And plus 2y lambda 1 plus lambda 2 j hat, right? And plus negative 2 z lambda 1 minus lambda 2 k hat, right? So we can make that like earlier. I hat corresponding I hat, j hat corresponding j hat, k hat corresponding k, right? Okay. So that would be 2x equal to 2x lambda 1 plus lambda 2 and 2y equal to 2y lambda 1 plus lambda 2 and 2z equal to negative 2z lambda 1 minus lambda 2, right? Okay. Now, let's make we have two other constraint functions, right? So normally we have a constraint function, we need to find x, y, z, right? Okay, let's bring the constraint function here. So we have the original one, copy, and we have equal to 0, 2. Yeah. Copy, constraint. Constraints. Yeah, I did not make a T earlier. All right, so let's what do you do? let's what we have to do next. Okay, lambda 2. So what we do lambda 2. So let's make equation 1, 2, 3, 4, 5. Equation number 1, equation number 2, equation number 3, equation. Actually, this is from the constraint, right? So it's a little bit different, but just a label for us, okay? All right, so from equation number 3, you can do anything. Lambda 2, solve for lambda 2. So that will be, we have that. Copy, paste. Okay, so lambda 2. So lambda 2 is negative. So move to the left side. Everything is the right side, right? So that will be minus 2 lambda 1 z minus 2 z. Yeah. Left side move to the other side. Okay. Now we do substitute into equation 1 and 2. That is equation 1, equation 2. You can do whatever you like. So equation 1 and equation 2. So there will be 2x equal to 2x lambda 1 plus lambda 2, lambda 2, lambda 2, lambda 2. So just copy. I wanted to make a different color, but let me just highlight. Copy. How about negative, right? So negative. Okay, now equation 2. So we have a 2y equal to 2y lambda 1 plus lambda 2. Just copy and paste. Yeah. And then highlight. We'll do that. Green color. Okay. This is lambda 2. Yeah. This is lambda 2. All right. Then what we do, let's just start for lambda 1 from the each equation. All right. So equation 1, we have that. Copy. So start for lambda 1. Okay, then lambda term make a right side and the others left side, right? So we will have 2x plus 2z equal to 2x lambda 1. Okay, let's factor out because we want to solve for lambda, right? So minus 2z, then lambda 1, right? So let's divide by 2 every term. So we have x plus z over x minus z equal to lambda 1, right? Okay, from the equation 2, we have, I'm checking the recording, whether I'm recording one correctly. Okay, equation number 2. Same processing, solve for lambda 2. I'm sorry, lambda 1. Solve for the 1. So we have, let's see, 2y plus 2z equal to 2y minus 2 lambda, no, factor out lambda 1, right? So z lambda 1. So divide by 2, so we have y plus z, and then divide by the other side, y minus z equal to lambda 1, right? Okay, now we knew that lambda 1 equal to lambda 1, right? So lambda let lambda 1 equal to lambda 1. So that will be 1 lambda equal to other lambda. So let's make the first one, this one, equal to other one. Copy. Equal to copy. All right. So then we can multiply this way, right? So we have x plus z, y minus z equal to x minus z, y plus z. Oh, we have to distribute, right? So the first term, xy minus xz plus yz minus z squared. We have xy minus x positive xz minus yz minus z squared. Please correct me if I make a mistake. Okay. Any combining like term. All right. So we make a negative xy. Then this is 0, right? And we make a negative xz. And there will be negative 2xz. Yeah, don't get confused with the 2 and z. 2, z. And then we make a positive positive yz, which is positive 2yz, and minus a positive z square is 0 then. Yeah, so this is 0. So this is 0. We have a z is 0. And the right side equal to 0, right? Black. All right. Z is common and 2 is common. So let's make 2z minus x plus y equal to 0. All right. So that means 2z equal to 0 or negative x plus y equal to 0, right? Okay. Now, let's make this way. All right, so if 2z equal to 0, that is z equal to 0, right? And we can say that also negative x plus y equal to 0, then y equal to x. Yeah. All right, let's bring the first constraint function. So let's take the original one. So what was the original one? So we have that. Let me using both because we need both later on. Copy? Because we want to solve for x and y, right? All right. So this is a constraint. So if z equal to 0, then x equal to 0, y equal to 0. There's only one possible, right? Think. For the first constraint function, right? But then the second constraint is not working. X equal to 0. Let me write down better. If z equal to 0, then x equal to 0, y equal to 0 for that. How about that, right? However, x equal to 0, y equal to 0, z equal to 0, not satisfied with second constraint. So that is 0 plus 0 minus 0 plus 1 equal to 0. 1 is not equal to 0. False, right? False statement. Okay. Now, what we are thinking, the second condition. So second condition, we had this one. Yeah. A little bit messy. Now, we have that. Copy and paste. So we have y equal to x. And then also we had the first constraint, right? So we have that. Copy that. Okay, then also second, right? So always let's bring the always both, because we have to use both, right? Copy, paste, make a shrink. Okay, now we have a z equal to x squared plus y squared. Then we can substitute y equal to x. So that will be substitute there. So we have a z squared equal to x squared plus x squared, right? Then we can solve for x. So we have z squared equal to 2x squared, right? Okay. We have to satisfy the two constraint function, right? In that case, I'm not using the function notation, so constraint equation, right? So how about here too? And x plus x minus z plus 1 equal to 0. There will be 2x minus z plus 1 equal to 0, right? All right. Now let's start for z for this one. Start for z. So we move to the z other side. So z equal to 2x plus 1 there, right? Okay. Now Since z equal to 2x plus 1, let's substitute into z here, right? Okay, so there will be 2x plus 1 squared equal to 2x squared, right? Okay, now we are using the formula 2x squared, which is 4x squared plus 2ab, 4 plus x is missing, plus 1 equal to 2x squared, right? So make the other side equal to 0. So we have 4x squared minus 2x squared plus 4x plus 1 equal to 0. Then we have 2x squared plus 4x plus 1 equal to 0. Okay, so we can solve for x, right? So this is not a nice number. We cannot using factoring method. So quadratic formula, how about that? So x equal to minus b plus minus b squared minus 4ac over 2a. Okay, so negative 4 plus minus 4 squared minus 4 times 8 times c or over 2a. A is not the 1, 2. Okay, now can you please calculate? So we have a negative 4 plus minus. You want me to write down everything? Square root of 8 over 4, which is negative 4 plus minus 2 square root of 2 over 4. So that is negative 1 plus minus 2 square root of, no, 2, 4 goes to 2 once. So there will be square root of 2 over 2, yeah? Okay, then we had y equal to x. And then z equal to 2x plus 1, right? So let's see using that. Let me share y equal to x. We have z equal to 2x plus 1. So let me just copy this one. Copy. So we have y equal to x. So y equal to negative 1 plus minus square root of 2 over 2. How about z, right? So we have a z. So z equal to 2x. Let's see using positive first. Negative 1 plus square root of 2 over 2. Just using plus minus. We can just using plus minus, yeah? So that would be substitute. Oh, we have a plus 1, missing plus 1. Oof, we must make a mistake. So that would be negative 2, right? Negative 2 plus minus, simplify this one, right? So we have a square root of 2. But then we have a positive 1. Then there will be negative 1 plus minus square root of 2, right? That's for z. So x, we have same as y. Z is different. So x equal to negative 1 plus minus square root of 2 over 2. Y equal to same number. z equal to -1 plus minus the square root of 2, right? Okay, let's find the local extreme values. So we need an objective function, and then I want to calculate. So objective function locally is not that crazy. Copy. How about here? Objective function. Almost done. This is the last one. Okay. All right. So we have f of. Let me copy. F of. Copy. Paste. Okay. So positive. Then let's make a positive first. Ooh. So that would be -1 plus square root of 2 over 2 squared plus -1 plus minus, no, minus, sorry, square root of 2 over 2 squared. I need space. Make it smaller here. Come on. Oh, let me make it. All right, so I arranged a little bit and then write out the z. Okay, so if we calculate this one, we have a 6 minus 4 square root of 2. You can use a decimal because it's hard to calculate, right? So that will be 0.3431. And then we're using negative part. So let me use negative. So negative. Let me turn off. Okay, so I changed the subtraction from the addition, everything. Oh, missing. It's not. Hold on 1 second. After I did. All right, so addition, from addition to subtraction, I changed that, right? Then we have 6 plus 4 square root of 2. Then we get 11.6569. So this is a local extreme value, right? So let me write down this one. Copy. So make a thus equal to that. Copy. And this one equal that. Local extrema. Okay, so let me correct what I said earlier. So in the beginning, I said, oh, let's find out whether this is a maximum or minimum, right? So when we find the maximum, minimum, we have to look for like a second derivative test, right? So we had the steps, right? So by the discriminant, blah, 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 whatever, right? And the center point, x, blah, blah, right? So we have to follow that. So that's why they give us a minimum. earlier for two problems. This one just a local extrema, right? So they say that local extrema of values, right? So find the values, not the whether maximum, minimum, right? Make sense? You understand what I'm saying, right? Let me change this one. So local extrema, right? So we're not bothering whether maximum, minimum for this one because we need to find only the value for this section. Make sense? All right, so local extreme values of the function, right? Objective function. Yeah. All right. Thank you for watching. I will see you in the next video. Bye. Where is it? Okay, there.